Hello and welcome to Lecture 3 of Gauss's Law in Phys 1204. In this lecture we're going to use our informal statement of Gauss's Law to come up with some very powerful statements about how charges behave inside conducting objects. By now you've come across the term equilibrium in quite a few different contexts. In Phys 1104, we talked about static equilibrium and dynamic equilibrium, and in your chemistry courses, no doubt you've talked about chemical equilibrium. Equilibrium always refers to a situation where nothing is changing. And so electrostatic equilibrium refers to a situation where a system of charges is such that none of the charges are moving or accelerating. In particular, we're going to be interested in conductors in electrostatic equilibrium. Now note that in conductors there are charges that are free to move. However, if the conductor is in electrostatic equilibrium, then they are not moving even though they're free to do so. And this can only happen under certain conditions. So let's think about a conductor. And let's say it's a metal. And here's an electron somewhere in the metal, and I'm focusing on the electron because electrons are free to move inside a metal. And let's say there's an electric field here, and I want to stress that this electron is not the source of this electric field. I don't know what is. Perhaps there's some positive charge over here, or some negative charge over here, or maybe some positive charge on the surface of the conductor over here. It doesn't matter. The point is that there's an electric field here, and because there are electrons everywhere in the metal, here's one at this location where we know this electric field. Well, what will happen to this electron? It's free to move, and it's at a location where there's a non-zero electric field. And electric fields cause charges to accelerate. Because the electron is negatively charged, it's going to accelerate in the opposite direction to the electric field. However, notice it's now accelerating. And so this conductor is not in electrostatic equilibrium. And what we can now say is that if there's an electric field anywhere inside the conductor that's non-zero, then the conductor can't be in electrostatic equilibrium because charges inside it will accelerate. So the E field must be zero everywhere inside a conductor that's in electrostatic equilibrium. This statement causes a lot of confusion for students. Note, I'm not saying that the electric field can't ever be non-zero inside a conductor. What I'm saying is that if the electric field in a conductor is non-zero, then that conductor must not be in electrostatic equilibrium. Also note that this whole argument doesn't apply for an insulator because the charges inside an insulator are not free to move. What happens if there is a non-zero electric field inside a conductor? So here's a conductor, and I've drawn positive and negative charges, and again, let's say it's a metal, so the negative charges are free to move. And there's an electric field that I've drawn everywhere, and so presumably somewhere outside the conductor here is some source of this electric field. We could call this an external electric field, or it's externally imposed on the conductor. Well, we've already seen that what's going to happen is that this electric field is going to cause charges inside the conductor to accelerate. In this case, it'll be the negative charges that'll accelerate because it's a metal. And so they'll move as a result. And because the charges in it move, and in particular it's only the negative charges moving, the conductor is going to become polarized. We've seen this. This is how polarization happens. Well, now think about the electric fields. There's still that external electric field being imposed on the system from some set of charges outside. But because now we have a bunch of negative charge here and a bunch of positive charge over here, the charges in the conductor are producing their own electric field that points in the opposite direction. Well, the charges in the conductor are going to keep moving until the electric field inside the conductor is zero. In other words, when this internal electric field and this external electric field exactly cancel each other. At that point, now the E field inside the conductor is zero, the charges don't accelerate anymore, and we've re-established electrostatic equilibrium. We don't have the tools yet to prove this, but I will say that later in the course we'll be able to show that this whole process of a conductor reestablishing electrostatic equilibrium is extremely fast. In most cases, it happens in nanoseconds or even picoseconds. So this fact that the E field inside a conductor in equilibrium must be zero has some other consequences, and in particular when we combine it with Gauss's law, we can figure out a few things. So here's a conductor, and let's say we've charged it, and it's in equilibrium. So in other words, we've perhaps transferred some charge onto this equilibrium, and then very impatiently tapping our toes, we've waited the whole few picoseconds or nanoseconds that it takes for the charge to all settle down, and none of it is moving anymore. So we have a charged conductor in equilibrium. The question now is, where is the charge on the conductor? How does it distribute on or in the conductor? Well, let's use Gauss's law to think about it. I'm going to draw any old arbitrary surface. So here is a closed surface entirely inside the conductor. Now I know that the E field is zero everywhere inside. And so that tells us that the electric flux through this surface must also be zero. Well, we know that the flux across the surface is proportional to the amount of charge inside the surface. And so what that means is that the total charge inside this surface must be zero. Okay, so I'm going to make the claim that that means there is no charge anywhere inside here. It's neutral everywhere. Now you might object and say, wait, Jeff, that's not really true. All you've proved is that the total charge in here is zero. So maybe there's some positive over here and an equal amount of negative over here. But I'm going to say, well, not so fast, because if that were true, then I could draw a new surface, say like this, but I know that the E field is zero everywhere in here, and so once again the flux has to be zero, and so there can't be any charge inside there. And so this idea that maybe there's just charge separation going on can't work either. And since I can draw any surface I want, and no matter what surface I draw, the total charge inside it must be zero, because the flux is zero, because the E field is zero, there cannot be any charge inside the conductor. But we've just said that the conductor itself is charged. So where is the charge? Well, it's not inside the conductor. The only place it can be then is on the surface. And so if, let's say, the net charge is positive, there must be a whole lot of positive charge out on the surface of the conductor. None of it can be on the interior. Now note what that means when we draw surfaces. I can draw a surface just inside the surface of the conductor, and again, the charge inside that surface is zero, and so the flux through it is zero. And so there's no E field passing through that surface. But if instead I draw my closed surface just outside the conductor, now all that charge on the surface of the conductor is in there, and so there is a non-zero flux. And that's telling us outside the conductor there is an E field being caused by all this charge that's distributed over the surface of the conductor. Now let's apply that same reasoning to a slightly more complicated situation. And because the situation may seem a little artificial, I'm going to tell you where exactly this sort of situation comes up. This is called a coaxial cable. And in a coaxial cable, there's some little wire that runs through the very middle, and it's surrounded by a gap that's non-conducting, and then there's another metal cylinder outside of that. So all of the orange here is conductor, and there's this gap in between. And often in the operation of a coaxial cable, there will be some amount of charge on this inside piece of metal and some other amount of charge, possibly positive, possibly negative, doesn't matter, on the outside. And so we often get these situations in technological applications where we have a charge inside a hollow conductor. So let's think about that. Here is a conductor, and I'm saying that this conductor is in equilibrium, and there's a cavity inside it. So all this hashed part is the conductor, and this part that I haven't hashed in is some sort of gap. And then there's some charge in the middle of this gap, let's say plus Q, some particular amount of charge. But additionally, the conductor out here has been charged and has a total charge on it, let's say of plus 2Q. So this could be a coaxial cable, or maybe this is a metal box, and we have taken, I don't know, something that we've charged by rubbing and put it inside the box and closed the box, and then we've touched the box with some other charged object to transfer some charge onto it. I don't know. There are any number of situations where this could arise. Again, the question is, where is the charge on the conductor? Well, let's think about a surface that we draw so that the surface is inside the material of the conductor everywhere. Well, again, the flux through this surface has to be zero because this conductor is in equilibrium, and so the E field is zero everywhere here. However, note, there's a charge. And so because the flux is zero, we know the total charge inside this surface is zero, but there's a plus Q here. That means there must be minus Q somewhere. Well, it can't be inside the material of the conductor, and so the only place it can be is on the inside surface of the conductor. And so there must be a total charge negative Q on the inside surface of the conductor. All right, but the conductor itself, we've said, has a total charge on it of plus 2Q. Well, we know it's got negative Q on the inside surface. There can't be any charge inside the material, and so all the rest of the charge on the conductor is on the outside surface, and so there must be positive charge on the outside surface. And furthermore, since the total charge on the conductor is plus 2Q, and it's got negative 1Q on the inside surface, it must have plus 3Q on the outer surface.